In this section, I'll take a closer look on the presence of error in numerical differentiation. Well, we've discussed quite some finite difference approximations of the derivative so far. For example, here on this slide, we see the forward difference, which we discussed was of order 1. So the truncation error is proportional to h. We have a backward finite difference. Again, truncation error is of order h. Or a central difference, which is a bit more accurate. So the truncation error is of order h squared. It's proportional to h squared. Now, and you might rightfully think so that the truncation error can be made arbitrarily small by letting h go to 0. So in that sense, I can simply choose h to be as small as I want. And then these terms will simply go away. Now, the truth is that the truncation error will reduce indeed when h goes to 0, but that is not the full picture. If you recall our discussion of errors in numerical solutions in chapter 1, we've seen that total error is always a combination of truncation error and rounding error. Now that rounding error will really start playing a role if we choose h to be a very small number. And we will dive into a bit more detail here today on how this affects our choice of h. So consider the following example. Let's say that we have a function f of x, which is a exponential function, and we want to compute the derivative of f at x is equal to 0 using a forward finite difference scheme as indicated over here. The analytical solution here, well, we can easily compute that. The derivative of an exponential function is simply the same exponential function, and plugging in x is 0 gives us e to the power 0 is 1. So we see that we can compute the exact numerical error between the true solution and our numerical approximation as follows. Now, if we compute this error for a large amount of values for h and try to find whether decreasing h leads to a smaller error, we come up with this somewhat surprising picture. And what we see here is, well, first note that this is in log-log scale. So in the y-axis, we have the total error, which is this term over here. And in the x-axis, we have h. So let's start from h is equal to 1, which by all means is a very large value for h. And we see that by decreasing h here, we decrease the total error that we're observing between the analytical value of 1 and our numerical approximation dh. And we actually see that this has a slope of 1. So this line has a slope of 1, which is corresponding naturally to our truncation error being of first order. So our truncation error is directly proportional to h. So if you plot it, if you set it out in a log-log plot, this will come out as a slope of 1. However, we see that at some point, further decreasing h leads to a very counterintuitive effect where the error actually starts going up dramatically as well. And this is something that's, well, unexpected if you only look at truncation error, but this is really where rounding error starts to come into play. Because when h gets smaller and smaller and smaller, we start subtracting here in the numerator of this finite difference formula, we start subtracting numbers which are closer and closer to each other, which we then divide by a very small number. So any rounding errors that we obtain in the numerator get amplified by this very small denominator. And this was one of the exceptional exceptionally bad circumstances for rounding error, when we were subtracting numbers that are close to each other and then also dividing this by a very small number. These rounding errors can really blow up. And that's actually what we're seeing over here. So let's try to take a closer look at the behavior of rounding error and truncation error in finite difference approximations for the derivative. So let's briefly restate the finite difference formula that we have over here. So what we try to do is we compute this function dh, which is f evaluated at two inputs that we define ourselves, so xi and xi plus h. Now in reality, because we have rounding error, we're not really computing dh, because we cannot really compute f at these points. They know they are, let's say, polluted by rounding error. And if you want to take if you want to revisit rounding error, then I suggest you rewatch the video lectures of chapter 1 or browse through chapter 1 of the book. But it's important to note that, well, not all real numbers can be represented into a computer, and that quite often, well, virtually always actually, these real numbers have to be rounded to the closest floating point, the closest floating point number that is available to represent in a computer. And we actually found that there is a certain tolerance, let's say, and we call it here epsilon, which can be regarded as a bound of this rounding error. And this epsilon is dependent on the machine that you're using, so how many digits precision that you have in your floating point representation of numbers. But it's also dependent on, let's say, the actual values of f of x. So for values that are close to 1, epsilon is, well, something like 10 to the power minus 16 in double precision. For f being much, much larger, well, then epsilon is also quite a bit larger. But let's consider here now that this rounding error is bounded by a fixed number epsilon, where epsilon is small, let's say, for practical purposes. So we consider it to be of the order of 10 to the power minus 16. Now we can try to take a look at the actual error that we're making by rounding these two values in the numerator. What is then the error that we're making on our finite difference formula d here? So what is the difference between dh and d bar of h? So we can try to express that mathematically. So we just take the absolute difference between d and dh, and you will see that, well, after some basic reshuffling, we can just plug in these formulas in here, and this will give you the following expression. So we see that this can be decomposed into a difference between f evaluated at xi plus h and the rounded value of f evaluated at xi plus h, and the same for f evaluated at xi with the rounded value for f evaluated at xi. What we do know is that if the argument here is the same, that we can provide an upper bound on the difference between these kinds of terms. So what we have to do is we have to split this entire this difference of these two terms into the sum of two absolute values of these form, such that we can convert this into something which has this form of epsilon. And for this, we can use the triangle inequality. And the triangle inequality, well, I just show it shortly here. It basically says that if you have the absolute value of a sum, this is always smaller than or equal to the absolute values of the individual components added together. And you can see that this is actually a triangle inequality, which actually states that in this case, A will always be smaller than b plus c. So the individual lengths of b plus the individual length of c will always be smaller than the straightest line from connecting the 2 points, which is a. So that's kind of a sidebar here. But the important outcome that we have observed here is that now we have split this rounding error into two components, where for each component, well, we can simply apply this bound that we have here. So we know that this guy on the left here, this is guaranteed to be smaller than epsilon, and also this guy is smaller than epsilon. So we have an expression for the rounding error, or we have at least an upper bound for the rounding error on our finite difference formula here. This rounding error, and it's important to take a closer look here, it will be smaller than this upper bound, and this upper bound is proportional to epsilon. So if you have a smaller epsilon, the rounding error is smaller, and this makes sense. If you have a more precise computer, if you have a more precise calculator, the rounding errors will be smaller. But this is inversely proportional to h. So this means that if you reduce h, the rounding error goes up. And this will depend on the relative value of h and epsilon. So epsilon is, for all practical purposes, small. So we can expect rounding errors to be small as long as h is not very, very small. And you see, this is where this kind of tricky idea of not picking h too small starts popping up, because then this rounding error really gets amplified. Error is not only rounding error, there's obviously also truncation error, which we've adequately discussed in the remainder or in the earlier parts of this lecture. And for a forward finite difference formula, the truncation error can be expressed as follows. So it is proportional to h, it's proportional to the second derivative of f evaluated at some xi in between xi and xi plus h. So we have now an expression for the rounding error and an expression for the truncation error in such a forward finite difference formula. So what we can say now is that restating our finite difference approximation, well, we have that the derivative is equal to the exact precision, so full precision finite difference formula plus a truncation error. But we cannot really compute this full precision one. We always have finite precision in our computations. So we can rewrite this as the rounded finite difference formula, which we actually compute in MATLAB, for instance, plus a rounding error, which we can specify as being bounded by 2 epsilon over h, plus a truncation error for which we can also derive an expression. So this means that we can group the error terms together into, let's say, a global error or a total error. So if we sum up this rounding error and the truncation error, well, we see that this total error, which is the difference between the actual value of the derivative and our rounded, truncated finite difference approximation of the derivative, again here applying some triangle inequality, this can be written as follows, for which we have here the rounding error, we have the truncation error, and for both of these we have expressions. So this means that we can express the total error as the rounding error plus the truncation error. So here we have a upper bound or an estimate for the upper bound on our total error as a function of epsilon, which is dependent on your machine, and h, which is a user-defined choice. So in conclusion, this was quite a derivation, and if it went a bit too fast in this video, I suggest you go through it with pencil and paper. But in conclusion, we found an upper bound for the error for this specific case where we use forward differences to approximate the first derivative on a machine with precision epsilon, and we found that this upper bound is equal to this. So we have a contribution of the rounding error, 2 epsilon over h, plus a contribution of the truncation error, h over 2 multiplied with the absolute value of the second derivative of the function evaluated at some point between xi and xi plus h. This might seem a bit abstract, so let's apply it to the specific example that we've been looking at in this video, and that was this exponential function. We were trying to evaluate the derivative at xi is 0. So that means that, well, xi will lie between 0 and h. So in that sense, the second derivative of f, well, that is e to the power xi, and that's a continuously increasing function. So we can, this abstract term, f double prime xi, we can also provide this with an upper bound, which is e to the power h. So in that sense, this leaves us for our current example with something that we can actually compute. So this is only a function of h. Epsilon is, let's say, a given. If you're using MATLAB and double precision, epsilon is about 10 to the power minus 16. And h is a parameter that you choose yourself. And you can try to optimize this for h and see which h will give you the minimum error. So let's take a look at our observations that we saw earlier and see whether our entire analysis of the errors, truncation error and rounding error, makes sense with the observations that we've seen. So here we have the actual error that we found. This is 1 minus the finite difference approximation that we did, the forward finite difference approximation. We can add to this plot the following terms. So what we have here is, well, we have this estimate for the truncation error, which had the following form, h over 2 times e to the power h, and that is this dashed orange line over here. We had an estimate for the rounding error, which is 2 epsilon over h, which we can also draw as a function of h. And here epsilon, I chose epsilon as being the epsilon of MATLAB, so that makes sense. And we see that the red line here is the sum of the rounding error and the truncation error. So this is our total error estimate that we made from our mathematical analysis of the error. And we did some simplifications here and there. We used some triangle inequalities and tried to define an upper bound. But what we actually see is that this total error estimate does quite a decent job in estimating the actual error. So this total error estimate, that's something we could derive without doing any numerical computation whatsoever. That's something we derived using pen and paper. But this corresponds quite well to the actual error. So we see that for large h, where the truncation error is really dominant. So here we see that the rounding error for h, let's say larger than 10 to the power minus 4. The truncation error is much larger than the rounding error. And we actually see that our error estimate is almost identical to the actual error that we observe. So the actual blue line is almost identical to the red line. We see that upon decreasing h further and further, this at some point, the rounding error starts to dominate. So this goes up. Whereas the truncation error, well, that goes down as we would expect. But the rounding error really starts to dominate. And we see that even here, well, we are off by quite a bit, but still we have a nice upper bound for the estimate of the total error. And the fact that the actual error is quite a bit lower is because of these things, these simplifications that we did on the left and right triangle inequality, which only gives an upper bound and not an exact value for this error. So this error analysis that we have done, actually, we could construct this red line without doing any numerical computation whatsoever. So this gives us an analytical formulation of the total error, and we could actually choose H such that this error is, let's say, below a desired tolerance level that we would want. You can optimize this for H, and in this case the optimal H would be somewhere around here where the total error is minimized. But we can choose H based on this total error estimate. However, an important observation here is that there is a lower bound on the error. So no matter what we choose for H, we will never attain an error, let's say below 10 to the power minus 10, using this forward difference scheme that we applied to this problem. Is that problematic? Well, that kind of depends on your application. If your application is very sensitive to these kinds of errors, it might be that you really want your total error to be of the order of 10 to the power minus 12. And then using the numerics that we applied in this example will really not work. It will really not cut it. And then you have to go for a different approach. So it's really quite important here that you also see that there is a lower bound on the error and that it cannot be further reduced by simply selecting a different H. Now, further reducing the error, this is actually a plea for these higher order schemes that we also discussed within this lecture. This is what you see here is the error for a simple forward finite difference scheme for this first order derivative. And we see that, well, the truncation error is of order H. So in a log-log plot, this truncation error shows up as a line with slope equal to 1. Let's take a look what happens if we, for the same problem, apply higher order schemes. So instead of a forward difference, we could look at central differences. And central differences, well, we've seen that these are actually of second order. The fact that the truncation error is of second order, that will imply that this line, where the truncation error is dominant, will have a slope of 2. So in this regime, when we reduce H, we reduce and reduce it further, the total error will go down with a slope 2 in a log-log plot. And this is really quite significant. So because in a log-log plot, well, the difference that we observe here for H is 10 to the power minus 5. We have approximately an error of 10 to the power minus 11, whereas here we have 10 to the power minus 5. So this is 6 orders of magnitude that our error is lower for this second order scheme than for the first order scheme. We see also that the slope actually where the rounding error is dominant is completely the same for both cases, and this has a slope of -1, because we saw that this rounding error has a form of something like 2 epsilon over h. And you can make a similar analysis for this central difference scheme, and also you will find that this has some kind of form times epsilon over h, and that's where this slope of -1 actually comes from. We see here that for the second order scheme, the minimum error is around 10 to the power minus 11, 10 to the power minus 12. If that's still not sufficient, well, we can go to higher order schemes even. For instance, a fourth order finite difference scheme, which is not explicitly derived here, but you can find it in the summary of finite difference formulas in the textbook. For this, we see, well, this corresponds to a slope of 4 when the truncation error is dominant. Again, a slope of -1 when the rounding error is dominant. And we also find that the minimum error here is even 2 to 3 orders of magnitude lower than for the second order scheme. So this is clearly a plea for higher order schemes when accuracy is important and when simply reducing h doesn't lead you to the desired level of accuracy.